This is Roger Green, host of the Surfing the NASH Tsunami podcast. This weekend, we are offering 5 conversations from Season 3, Episode 35, our final wrap-up episode looking at basic liver science presentations from the International Liver Congress 2022. Episode 35 reviews 6 basic liver science presentations related to fibrosis that took place at a session of ILC 2022, chaired by Scott Friedman. Scott joins us to lead the discussion on these presentations, while Neil Henderson and Rachel Zayas join the regular surfers to provide their own perspectives and ask good questions. This conversation looks at 2 presentations exploring the relationship between stellate cell performance and fibrogenesis using omics methods, some of which were first described by Neil and his colleague Prakesh Ramachandran. Along the way, Scott, Neil, and Rachel discuss some of the subtleties of omics and how they work in these situations, while Jorn Schattenberg and Louise Campbell ask questions from a clinical perspective, and I ask again about commercial implications. These conversations cover some challenging and exciting issues in basic liver science. They point towards continued explosive increases in what we understand about NASH and fibrotic process in the liver in general. So sit back, listen, enjoy, learn, and when you're done, join the dialogue on our LinkedIn discussion group.
Scott Friedman.
So although I've chaired many sessions over the years, this was one of the most exciting groups of presentations I've seen in many years. I don't know if it's because the science is just maturing, getting better, and or because there could have been a lot of pent-up, interesting data that just is waiting for presentation. But whatever the reason, I was really jumping out of my seat from all the novelty and the state-of-the-art methods that were used, all of which has a lot of translational potential, none of which is directly addressing treatments because those were the focus of other sessions. So in no particular order, I'm just going to give you an overview. I think some of the conceptual advances included using induced pluripotent stem cells to recreate stellate cells, tracking, and I'm going to go through these in details, of course, tracking the proteomics of different cell types to identify new therapeutic targets, uncovering a circadian clock within hepatic stellate cells, which, to remind you, are the fibrogenic cells in liver, beginning to zero in on the dynamics and the cells regulating matrix degradation in fibrosis regression, and some new insights into how bile ducts get sick and start proliferating when there is injury.
Scott, why don't we go on to 1 or 2 other of the papers you'd like to cover next?
So let me focus on 2 abstracts that are right in Dr. Henderson's wheelhouse, as we say here in the States, and that is the use of single-cell evaluation of gene expression. So let me just back up and say that Neil and his colleague Prakesh Ramachandran have been pioneers in this field. They published a landmark paper in 2019 in Nature that really set the stage, as other similar papers have done in other organs. And Neil can probably explain this better than me, but what we're literally doing is taking individual cells from a tissue of any type, and in our case liver, and interrogating the transcriptome or the output of mRNAs from all the cells. And then we can use very powerful informatics to define the different cell types as they were in vivo and infer from that relationships for how the cells talk to one another, how they behave, how they change in disease or in development. And I would say that, to me, having been in the field for a pretty good time now, this is the only technology that's remotely as transformative in my experience was PCR, polymerase chain reaction, which opened up a whole new world of diagnostics, of course, and molecular biology, and really exploded the field. That too won a Nobel Prize, and as did another revolutionary technique that hasn't been so widely used in liver, and that's CRISPR-Cas9. But back to the single-cell sequencing, one can either do this by taking a piece of frozen liver and isolating the nuclei and measuring the mRNAs within the nuclei, or you can take fresh tissue, which is what Neil has published mostly, and separate the cells, clean them up, and then put them through a sequencer. So I want to give Neil the platform in just a second, so I'll just mention 2 articles briefly. Well, I'll just focus on one, the stellate cell dynamics in progression and regression of hepatic fibrosis. So to set the stage here, we know now very well from the success of hepatitis C therapies that even if you have a patient with advanced scarring, if you cure their hepatitis C, or in the case of hepatitis B, if you substantially suppress the virus, you get regression of scar. So the liver clearly has a way to eat up or degrade that scar and help return the liver to a normal state. And in the case of antivirals, what's so fascinating is those drugs are doing only one thing, and they're eradicating or suppressing the virus. And yet the whole liver resets and begins degrading scar. Neil's, I would say, his academic grandfather, actually his academic father, John Iredale, did some seminal studies we were involved with many years ago, in which we began to say, well, where's the enzymes coming from in these cells that must be present that are degrading the scar? And we made some modest headway, and the implication from those studies was it's either macrophages and or stellate cells themselves that are making most of the proteases. And then we kind of moved on, and it has been surprising and in some ways now gratifying that we had first overlooked but are now applying these very powerful single cell sequencing methods to begin to go back to those original observations and say, where are the cells that are making these enzymes that chew up the scar and help return the liver to normal? And what are the signals that drive that process and that also help restore hepatocyte health? And so that was the basis of the study presented by El Almala del Barrio, who I think was from Spain. I don't remember her institution, in which the work was supported in part by Novo Nordisk. And they're beginning to catalog how the cells respond when you stop injuring a mouse liver. And, we're actually taking a similar approach. I have a feeling Neil may be as well, because this is so important. If we can understand the signals and the cells that return this liver to a healthy state with no scar, we can obviously try to exploit those to develop new therapeutic targets and reverse fibrosis. So with that long preamble, Neil, can you help us understand this better?
Neil Henderson.
Thanks, Scott. Yeah, I echo all of what you've said. In some ways, it is very surprising how much this element of fibrosis biology in the liver and in other organs has been overlooked somewhat. There's been a lot of focus on the bad guys making scar. There's been a lot less focus on how we can manipulate the pathways that degrade scar and return the liver to normal architecture. Understandably, most of the studies have been rodent-based because you can model fibrosis to peak fibrosis and then remove the injurious insult and watch scar melt away. Mice are very good at melting scar, but in humans that's been more challenging to study. And I think deployment of the single-cell technologies that Scott mentioned could be really, really helpful in trying to work out how this process is happening in human liver disease. The issue is getting tissue from patients whose fibrosis has resolved, because clearly you ain't going to be sticking needles in people's livers if their liver is getting better. But I think there are ways we can start to get at that, but that's all nascent in the field. But I totally concur. Looking at not only the cellular players involved in collagen breakdown, but actually the biology of collagen and how that might be degraded at molecular level. There's some nice work around the world looking specifically at those types of pathways, but I think they have been overlooked. The other thing we need to think carefully about is, can we ever hope to degrade fully cross-linked, very mature collagen? Is that beyond the reach of even our wildest dreams of therapeutics? It's very dense in the middle of a big fibrotic septum and a cirrhotic liver. Are we ever going to achieve that? I'd love to think we might, but that I think is a high bar. But I guess even if we can initially arrest fibrosis progression, that's potentially, or would be, a win for the patient who's, say, at F3 or F4 fibrosis, because we know that will reduce the risk of complications. So yeah, very interesting area. I hope it gets more airplay in the coming years. It's been overlooked so far. The technologies that we mentioned are going to open this right up again, but at a resolution we've not had before. So it's exciting.
Neil, is this something that would be additionally elucidated by spatial transcriptomics? And maybe if so, describe for us what that is.
Sure. So yeah, I agree. I think it could be. So spatial transcriptomics is a absolutely blossoming, rapidly evolving field. I mean, single cell genomics as a whole is rapidly moving, but spatial is just going wild. And it's great to see, both as a user of the technology, because it's exciting and it's telling us things we couldn't see before, but also there's a lot of competition in the space. And just to explain that to people who totally understandably have never heard the term, the reason that we're excited about spatial transcriptomics is that when you do single cell or single nuclei sequencing, you have to break the tissue down into single cells or single nuclei. So henceforth, you've lost all feel for tissue architecture because you've broken the tissue up into single cells. Spatial transcriptomics is a step change because it allows you to do on tissue section, on slide, in situ genome-wide sequencing. So this preserves all the relationships that all the different cell types have in the fibrotic niche, for example, in human liver fibrosis, and it allows you to measure gene expression at a genome-wide level across the entire section. Now, currently, we're at about 50 micrometers spots of resolution with one of the leading commercial solutions, but that obviously includes maybe 10 up to 15 cells in the liver. So we can deconvolve that data with clever informatics approaches to try and work out where the genes within that spot are coming from, but we're going to get towards single cell resolution probably early next year with some of the commercial solutions coming through. And I'd just add that what I find super cool about this approach is when you anneal to the array to measure all the gene expression, each spot has unique barcodes. So you can then take all that, make it up into a solution, send it off as a cDNA library for sequencing, and then the informaticians can work out exactly where each gene came from within each spot on that array. So as the array comes down to single cell resolution, we will be able to say that cell is expressing those genes and its friend next to it is expressing those genes because we've taken a picture of the tissue before we even did any of this. So you can work it all the way back in a big closed loop back to the original tissue. So you can imagine that in the cancer field, in the fibrosis field, any area of biomedicine, spatial profiling is absolutely massive. And as Scott's alluding to, what that should be super helpful for is target discovery, because you'll be able to ask questions about ligand receptor interactions and actually verify that they are appropriate in terms of that cell expressing X is next to that cell expressing Y, and we think it's druggable and we think it's relevant because that cell is a certain type of cell and that cell is a certain type of cell. So really exciting genuinely really exciting technology.
Jörn Schattenberg.
It is fascinating. I'm just going to say something quickly again. I know Rachel probably has a comment on this too. Is Neil, in that paper they talk about 14 diverse hepatic stellate cell populations. Now that probably means that we have, the hepatic stellate cells is one unique cell populations, but I understand they're in different states of, let's say, activation, and they're transitioning through that is my understanding, and that's what they're able to measure. And you're saying that depending on what stage of activation they're in, they have different signatures, and that could be druggable. And then maybe you have to look for the dominant feature, or how is maybe you can post this a little bit from the clinician's point of view. I have one patient, one liver, but they have so many different subtypes or subpopulations of hepatic stellate cells. How do I bring that together for one patient? Is there going to be a dominant one that I want to drug? Is there a dominant one that drives the phenotype? Or maybe there's the little tiniest population, but that's the most critical for the patient. So any thoughts on that, or how can I put this in the whole of the patient? I mean, for drug discovery, that's an interesting theme.
Yeah, great question, Jörn. And this kind of brings me to the devil's in the detail with single cell data. And I know you'll be aware of this, but it's really helpful for us to kick this around and chat through it. So you can cluster your data in various ways. You can take an amorphous blob of single cell data and you can literally change the amount of subclustering your informatics analysis will show. So you could take a blob and turn it into 12 clusters or 4 clusters. And it's all to do with, how you approach that with your algorithm. Now, what I would say is, and maybe this is old school even within single cell, in our group, we don't really believe that there are different subpopulations until we've validated it at the protein level in some way. That's the approach we take. Different groups are different, but, if I was proposing, now this is where the semantics are important. If I was proposing 14 different stellate cell subpopulations, I would like our wet lab guys to try and validate that in tissue. Now, subpopulations, one could argue, are different from cellular states, and that's a different kettle of fish. But annotation of cell state is actually really quite difficult, to be able to say with confidence that, for example, there are 14 different cell states within the global stellate cell population. So I would be inclined to say, as I've mentioned, I'd want to see validation of clear subpopulations before, we pursued that as our group, but many people are taking different approaches. Because you're right, a key question is, what's the key pathogenic subpopulation, and hence is the one you want to try and drug, and hence what are the unique features about that subpopulation that would allow you to drug that and not affect mesenchymal homeostasis, which, lest us not forget, a lot of these patients have very brittle background liver function. The last thing you want to do is disrupt normal mesenchymal homeostasis. So it's a key point you raise. And it's something the field is still working with. We all are, as to how best to approach that initial clustering and then validating it afterwards.
Just to close out the discussion around matrix degradation, there was a presentation looking at a subset of macrophages and the role of an antioxidant known as peroxidase by a young scientist from Mass General Department of Surgery. Her name was Mozdes Sojuji, and she had very interesting both animal and culture data that implicated this pathway in reprogramming macrophages to make more or less scar-degrading components. So it just speaks to the idea that there is a concerted effort now to turn back or go back to the key question of where the enzymes come from and what they do and how they're regulated to melt scar, to use Neil's term.
And now, back to Roger.
We hope you've enjoyed this recording. If you have any questions or comments about the content of this conversation or the entire episode, please send an email to questions@surfingthenash.com. We'll be back next week with a new episode of Surfing the Nash Tsunami on Wednesday, July 13th. I'm pretty sure I know what we're going to talk about, and it's a major news story, but we haven't completely firmed it up yet, so I'll leave you in suspense. Until then, stay safe, surf on. We'll see you on the podcast. Bye-bye now.